Hey guys, today we will be going into a new topic, which is the basis of probability. The first thing that you should know is some basic vocabulary words. The first of these is sample space. So this is all of the possible outcomes that you could get, and it's denoted with an omega. So the Greek letter omega, it looks like this. And so when you write out a sample space, you would say omega is equal to, and then you list out your set of all the possible outcomes. For example, if we were flipping a coin, our possible outcomes are heads and tails, right? So our omega would be equal to H for heads and tails, and that would be our entire set of outcomes. Next we have our trial. So it's every time we go through with a random event and get some outcome. So every time we flip our coin, that will be one trial. Next we have the outcome, so that is what we get from the trial, that is our actual heads or tails. And then we have two types of probability. The first is theoretical probability. This is basically the hypothetical probability of an event occurring. So the theoretical probability of getting a heads when flipping a coin would be 50%, because there is one way to get heads and there's two total outcomes. So it's 1 over 2, which is 50%. Then we have our observed probability. So this is the probability that we get from actually carrying out an experiment or a set of trials. So if we flipped our coin 3 times and we got heads on 2 of them, then our observed probability is now 2 over 3, which is equal to 66.667%. So what you have to note here is that theoretical probability does not usually equal your observed probability unless you got really lucky or something. So there's 2 general rules that you need to keep in mind. The first is the law of large numbers. So what it says is that as you keep running your trials over and over again, the observed probability will get closer and closer to your theoretical probability. So if I flip my coin once and I get a tails, then our observed probability is 0% heads. If I flip it again and I get another tails, then it's still 0% probability for heads. But if I flip it again and I get heads this time, our sequence of events has been T, T, and then H. So our observed probability has become 33%. And as we keep on going, the observed probability should increase towards our theoretical probability. In most cases, if you graphed out the probabilities with the number of trials being at the bottom, and then the probability being up here, then these usually end up oscillating until they center around some line that is the theoretical probability. So here, if this was our coin toss, this would be our 50% line, and then you can see the probability slowly start to approach or 50%, so our theoretical probability. Next we have our law of averages. This law does not exist, but it is a mindset that a lot of people tend to hold. It basically says if you're on a streak, the streak is either bound to end or the streak is bound to continue, one of the two. The way this shows up a lot of the times is, let's say you have a married couple and they have had 5 sons in a row, and then the dad says, because we have had so many sons, we're bound to get a daughter next. And then the mom says, because we had so many sons, the next one's just going to be a son too. So both of these parents clearly show the law of averages mindset. And this is false because each trial does not affect the other, so it's still a random probability. Nothing is really bound to happen. Next we have independent versus disjoint variables. So when 2 events are independent, that means one does not affect the other. So the outcome of one event does not affect what the outcome of another event will be. Getting heads on one coin toss will not affect if I get heads on the next coin toss. Now for disjoint, this is when 2 variables cannot happen at the same time. So this is when, let's say, we're talking about 50% of the time I am at home and 50% of the time I am at school. If I am at home, I cannot be at school at the same time. So that would make being at home and being at school disjoint variables. And when 2 variables are disjoint, this makes them not independent. The main difference between independence and being disjoint is that disjoint variables cannot be independent. So that's kind of counterintuitive, but if you think about it this way, let's say we have event A and event B. By the rules of independence, if A and B are independent, whether A happened or not should not affect whether B happens or not. Keeping that in mind, let's just say for now that A and B are disjoint, so that means A and B cannot happen at the same time. Theoretically, the probability of getting each one is 50%. Again, these two events cannot happen at the same time. Each of them have a 50% probability of occurring. So let's say event A has occurred. But because these two events are disjoint, that means that because A has occurred now, that means that B cannot occur now. So this 0.5 turns into a 0 because these are disjoint and therefore A and B cannot happen at the same time, which changes our probability to 0. So that violates our independence because the outcome of A has affected the outcome of B, or whether or not B happens. So here are our basic probability rules and symbols. Theoretical probability, which I've mentioned before, is equal to the number of ways to get your desired outcome over the total number of outcomes. So back to our coin toss, there's one way to flip a heads, and then there's 2 total outcomes, so it's 1 over 2, 50%. Before we go into the next 2 formulas, there are a couple of things about notation that you guys should know. The first is that P of whatever, this does not mean multiplication anymore. This does not mean some variable P times whatever's in the parentheses. This P and then parentheses means probability of. So P and then of A would be equal to, if you read it out loud, probability of event A occurring. Next, there's this weird U thing, probability of A, U, B. This U here means or. So if you read this expression out loud, it would be the probability of A or B occurring. So coming down here, we see that when events A and B are disjoint, then the probability of A or B occurring is equal to the probability of A plus the probability of B. So whenever you see your U for union, that means you have to add. So next we have another similar notation. Again, it's P, and then now we have a upside down looking U, and then B. So how this is read is, this symbol is read as an AND. So this whole expression would be the probability of A and B occurring. Coming down here, we see that when events A and B are independent, the probability of A and B occurring is equal to the probability of event A times the probability of event B. When it comes to probability, drawing out diagrams and charts to help you is really helpful. So we have an example here. Let's say 60% of students on a college live on campus, 40% eat at the school cafeteria, and 30% do both. The first thing we observe is that these two are not disjoint, so these two can happen at the same time. So making our Venn diagram, here's a basic structure of what it should look like. We have our 2 circles here. What this box on the outside represents is our entire sample space. So inside of this sample space is 100%. Some of the 100% is in here, some is in here, some is in here, and there's still some floating on the outside. The probability floating around on the outside represents the students that do not live on campus and do not eat at the school cafeteria. So how do we find the probabilities for everything? The first thing we do is start from this number, so 30% do both, because this is the one thing that we can fill in right away. So 0.3 goes in the middle here for students that both live on campus and eat at the cafeteria. Now we have to find the probabilities for cafeteria only and living on campus only, but not both. So we know that 60% of all students live on campus, but we already see that 30% has been taken in the students that do both. That means that outside of this 30%, there's still another 30% out here. So everything here should add up to 0.6. Next, coming over here, we have 0.3 of all the students, both living on campus and eating at the school cafeteria. But we know that it's actually 40% that eat at the school cafeteria. So that leaves 0.1, so 10% of students who only eat at the school cafeteria but do not live on campus. So what's left outside in our sample space for students that do not live on campus and do not eat at the school cafeteria? This is easy to calculate now because we have all of our numbers listed out here. Out of 100%, this many students either live on campus or eat at the school cafeteria or both. So we just have to subtract this number from 100% to find our remaining students that are outside in the sample space. So we have 0.3 plus 0.3 plus 0.1, which is 0.7. So that leaves 30% of students who do not live on campus and do not eat at the school cafeteria. So now if I were to ask you, what percent of students eat at the school cafeteria but don't live on campus, that would be our number here. So this is a really good tool to look at whenever you're referencing some more complicated probability questions. Next, we have a general addition rule. So going back to the first addition rule that we learned, it was only for when events A and B are disjoint. So what about when they're not disjoint? What if A and B can occur at the same time? So that is what we have here. The probability of A or B occurring is equal to the probability of A occurring plus the probability of B occurring minus the probability of A and B occurring. This formula is actually the same as the one up here. It's just missing a third term, right? These formulas are the same in that when events A and B are disjoint, then the probability of A and B occurring together becomes 0. So one is basically derived from the other, but this one is more applicable to other situations. So putting this into practice, we have an example here. If 57% of people in a city have dogs, with 23% of people in the same city having cats and 14% having both, what is the probability that a person has a cat but no dogs? There's two ways to do this. The first is to draw another Venn diagram, but we're going to try the formula first. So here our event A, let's say it's having dogs, and event B, let's say is someone having a cat. The question does say what is the probability that a person has a cat but no dogs, but we'll start with a different one first to use our new formula. So we'll go with what is the probability that a person has a dog or a cat. So this includes people that only have dogs, people that only have cats, and people that have both. So dogs, cats, or both. So the probability of that would be the probability of dogs or cats, or we could write probability of A or B is equal to the probability of someone having a dog. So P dog plus P event B is having a cat minus the probability of dog and cat, which is equal to 0.57, which we get from up here because 57% of people have dogs, plus 0.23 for the percentage of people with cats, minus the probability of them having both. So that is equal to 66% or 0.66. If we wanted to go the other way and make this into a Venn diagram, we would have something that looks like this. So we have our big sample space, we make our circles. Let's say this one is for dogs, and this one is for cats. And we know that 14% have both, so that leaves 0.43 in the dogs only, and then 9% in cats only. So now if we ask the probability that a person has a cat or a dog, we would just add up these three numbers here and we would get the same thing, 0.66. Now coming up here, the probability that a person has a cat but no dogs, we can also get that from this box right here. So cats only, 9%. So we have this thing called conditional probability. And it says that when event B occurs, what is the probability that event A occurs? That is how this line is read as. It is read as the word given. So the probability of event A given event B is equal to the probability of A and B occurring over the probability of event B occurring. So if you want to remember this formula, you can see this line here as a sort of division sign. So you know that the B goes in the denominator. Using that, we also have a general multiplication rule, which is derived from this formula. You just have to rearrange your terms around. So we get the probability of A and B occurring is equal to the probability of A times the probability of B given A. Putting this into practice, we have the same scenario again, but different question. So what is the probability that a person has a dog given that they have a cat? So first we write that into our probability notation. So the probability that a person has a dog given that they have a cat. So our formula for this one is the probability of dog and cat, so A and B, over our second term, so probability that they have a cat. So we know that the probability that a person has a dog and a cat is 14% because the question says that 14% has both. And then we divide it by the probability that they have a cat, so 0.23, and we get 0.6087, so 60.87% chance. There is one last way to represent probability problems, and this one is used the most whenever you have layered probability questions. So one example of this usually comes in disease testing. In this case, to go with a more realistic example, we have COVID-19 testing. So hypothetically, let's say out of the population, 1% of people have COVID-19. When we test people for COVID-19, there is a 2% false positive rate. So that means if you go and get yourself tested and you don't have COVID, but the test says you have COVID, that is a false positive. So it falsely says that you tested positive. So a 2% false positive rate means that 2% of people that don't have COVID will test positive. And then it also has a 97% accuracy rate. So this means that it will detect 97% of people with COVID. So if you have COVID, there's a 97% chance that if you get tested, it will come out as positive. Now we want to know that the probability of someone having COVID and them testing negative. So the best way to do this is always to draw out a picture again, so we can do a tree diagram. So first, we put our entire population as our big pool of people, and then we're going to branch out from inside the population. So first, we have to go with the percent of people that have COVID or not. So we know that 1% has it, so we'll put that up here. 1% of people having COVID, and then 99% not having COVID. Now, let's say everyone goes and gets tested. So out of the people that have COVID, we know that there is a 97% accuracy rate. So 97% of them will be found as positive for COVID, and then 3% will come out negative even though they have COVID. So this is our tests problem. Now, out of the people that don't have COVID, 2% will test positive as a false positive, and then 98% will test negative. So we want to know the probability that someone has COVID and tests negative. So the way you go through this tree now, you can just multiply across the lines. So the probability that someone has it, so 0.01 times the probability that they test negative, so 0.03. And from there you get 0.0003. So probability negative given has COVID is equal to 0.0003. Now instead, if we just want to know the overall probability that someone tests positive, we can still use this tree, and it shows how powerful these tools are. So we have two ways to test positive here. One is a false positive and one is a correct identification of someone with COVID. So the way we could find the overall probability that anyone tests positive regardless of whether they have COVID would be 0.01 times 0.97 plus the other probability of someone testing positive, so 0.99 times 0.02, which would be equal to 0.0295. And that is it for basic probability models. In the next video, we will be going over models for random variables. I hope you learned something. Peace.